Alright, let's talk about question 4, which addresses this song contest that Mickey and Anna are very enthusiastic in, so passionate that they decided to predict the true scores of each country in the contest. So now we're given a vector that stands for their prediction, one being Anna's, one being Mickey's, and then the third vector being their true total scores, also expressed in a vector of the similar dimension. But the true score has an unknown component. So if we want the magnitude of error of Anna's prediction and the magnitude of error of Mickey's prediction to fit this inequality such that the error from Professor Anna is less than the error from Professor Mickey, what are the possible values for this unknown component, which we denote as the Greek letter alpha? Let's try to formulate this problem mathematically. So we are facing the inequality that could also be in matrix expression be written as something like this, where the magnitude of P Anna and P truth's error squared is less than the magnitude of prediction from Mickey minus the true score. And this magnitude is also squared. It is really component for us to see the magnitude square because this square of the magnitude of a vector is the inner product of a vector with itself. Okay, so now that we have this aside as our special tool that we'll use later, let's try to simplify the inequality down. So we're just going to do some math for the difference between vectors, which will grant us something like this. And so now we just need to take the inner product of these vectors with themselves, which gets me something like this inequality. And then I also have to inner product the other side with itself, so it also gives me something like this. So I'm going to skip some steps of math because I believe in the ability to calculate something in my mind. Okay, so I have this inequality now. And now I'm going to simplify it further by crossing out a alpha squared from both sides, and I'm also going to subtract each side by 105. I'm also going to add each side by 26 alpha, which will then grant me an inequality that looks like this, and grant me that alpha is larger than 11. So what this inequality is telling us is that as long as alpha is a number that's larger than 11, this inequality will work. So the possible values for alpha is any number that's larger than 11, or we can express the set of all possible values as any real number such that it's larger than 11. Okay, so these are just two ways to express the same mathematical fact, except one is using a more compact notation while the other is only using text. For now, both will work, and the one that only uses text will work better for compactness and conciseness. But in an exam, we actually just have to show the inequality here, and that will work out, since that is actually where the solution terminates. So now let's look at the second part of the question, where we now have this matrix such that for I is equal to 1, 2, and 3, AVI is equal to lambda VI, which means we have this eigenvalue-eigenvector relationship, And our objective of the question is to get the vector P, which is the result of a matrix multiplication A times the vector 3, 2, 1. So since we're not directly given the values of A, we cannot use the like this, like that explicit matrix multiplication method. However, we do have the eigenvectors of A, so if we can find that 3, 2, 1 is equal to alpha v1 plus beta v2 plus gamma v3, or in other words, if we can find 3 to 1 as a linear combination of the eigenvectors, then we can say that A times 3 to 1 is equal to A times this linear combination. And then, since A is multiplying its eigenvectors, I can directly translate that to its eigenvalue multiplying its eigenvectors, which will then give me the expression that is a linear combination expressing the result of A times 3, 2, 1. And since we know the value of lambda 3 and v3 and the eigenvalues and the eigenvectors, we can directly express this linear combination as a single vector and thus find the components of this vector P. So there's only one thing or one set of values that we need to find now so that this expression is entirely known. And that would be the values alpha, beta, and gamma, which are the coefficients in this linear combination. So I need to find that 3, 2, 1 is equal to alpha times the first eigenvector, which is 1, 0, 1, plus beta times the second eigenvector plus gamma times the third eigenvector. So now we have two ways out of this to get the values. The first way is the most surefire way, which is that we construct a matrix vector multiplication system out of this. Let me write this clearer. This is equal to 3, 2, 1. And then we can try to solve this system to actually get what values alpha, beta, and gamma should be. Or the other one is that we mental math this out again. And mental mathing gives me, so I'm going to try using the first eigenvector first, and I know that since the third component is only 1, I can only use one of the first eigenvector so that my third component stays to be 1. And then I can also add 2 of the second eigenvector. And actually that would just directly yield me 3, 2, 1. Mental math is not a surefire way. Please do not do this on the exam and do the Gaussian elimination instead. But now, through some very fortunate lucky math, we know that alpha is equal to 1, beta is equal to 2, and gamma is equal to 0. So now let's reuse this linear combination we got up here for calculating A3 to 1. So this will be equal to 2 times, and then I know that the eigenvalue lambda 1 is equal to 6. So this is, this is 1. 1 times 6 times the first eigenvector plus, and then I know that beta is equal to 2, but lambda 2 is equal to 0.5, so 2 and 0.5 cancels out to be 1, and then since I'm never using the third eigenvector as my component in the linear combination, I'll just give it up. And so now I get this vector that should follow some form like this, which gives me 7, 1, 6. And this is going to be equal to A times 3, 2, 1. So now that we have solved part B with some eigen stuff, we just have part C left, which tells us that our voting system has been corrupted. So the corrupted total points we obtain is in this vector, which is P corrupt. I'm just going to write it as PC for shorthand. And we are also told that the uncorrupted points should be such that the vector is about 2n, n, n, for n being a real number. such that PA is equal to 2PB, that's satisfied, and PA is equal to 2PC, and PB is equal to PC. Okay, so in other words, the uncorrupted point should belong to the span, this vector should belong to the span of 2, 1, 1, or in other words, should have the direction of 2, 1, 1. So let's review what we're having again. We have P corrupt, which looks something like this. And then we also have a true direction that is uncorrupted. And then we're trying to find, given these vectors, a vector P star that satisfies the uncorrupted vector condition, which is that it has to have this direction 2, 1, 1, while being closest to the original corrupted points. So actually we're finding a projection of the corrupted vector onto the direction we want, or the condition, or the constraint that we need to satisfy. And we also need to be closest to the P corrupt, which is why we're projecting the vector P corrupt onto that direction. So now we have to calculate this this projection, and we have to remember the projection formula, which is derivable via some geometry, but it's always easier to remember it anyways. So I'm going to write out the formula, and then since this is in the direction of 2, 1, 1, it will naturally be that we multiply this magnitude by 2, 1, 1. Okay, so now we have to calculate the inner products. The inner product of 2, 1, 1 with itself is going to be, let me see, 4, 5, 6. Okay, and the inner product upstairs is 2 times 20 plus 1 times 15 plus 1 times 5, which will be 60. And then we have to multiply this by the vector that we are projecting onto, or the direction that this vector that is uncorrupted should have. So we get that the final result is 10 times this direction, which gives me 20, 10, 10. So this will be the vector that satisfies the constraint, which means it has a direction of an uncorrupted square while being closest there can be to P corrupted. And that is actually the definition of projection, which is why we use the projection vector. And so in the end, we again get the result that this new projected vector should be 20, 10, 10. And thus we have ended this question.